Of course, as we have seen, parallel computing is not new and has been around essentially since the early 80s, and databases have also traditionally evolved to exploit parallel computing over the years. In the beginning, we had shared memory databases, which still persist to date, where you have a large multiprocessor system with multiple CPUs sharing memory, a single operating system scheduling jobs or processes across these different CPUs, and a common disk or storage area network where all the data is stored. Examples of such systems abound. Almost all servers today are multiprocessing shared memory systems, but they at most a few dozen processors, and even with each of them having multiple cores, we find shared memory systems supporting at most a few hundred processing units. The shared memory model simply doesn't scale beyond this level. Databases have exploited other parallel architectures such as the shared disk architecture and the shared nothing architecture, which scale to greater number of processors as compared to shared memory. In a shared disk architecture, you may have multiple processors which communicate over a network, accessing, however, a common disk system, which could be a storage area network or a network attached system of storage, using two different networks, one for communication between processors and the other one for accessing storage. The shared nothing architecture, on the other hand, relies on local disks with each processor, so that the only communication that takes place over the network is between processors. In a parallel database, in both the shared nothing architectures as well as the others, SQL queries are executed in parallel by multiple processors. In the shared nothing architecture, in addition, data itself is distributed across different disks using varieties of partitioning schemes, such as different sets of rows on different disks, or in the case of column-oriented specialized engines for analytical processing, different sets of columns on different disks. All this has happened in the database community, and parallel databases are now almost a given. They all support SQL. Some of them support transaction processing, where of course there's the additional overhead of managing transaction isolation and consistency across multiple processors, but we won't get into that right now. The thing that is not handled by parallel databases properly is fault tolerance. They didn't have to handle fault tolerance because with just a few dozen processors, you don't need to worry about processors failing while executing a SQL query, which anyway will take a few seconds or a few minutes at most. But when you're executing a large batch job which touches virtually all the data, the chances of a processor failing are very high, especially if you have a large number of processors. And in such situations, the parallel database architectures simply are not fault tolerant. Fault tolerance in the parallel database world relies on having a hot standby architecture or a deployment which is identical to the primary and essentially replicating data over a high-speed network between the primary and the hot standby, a very costly and still not completely fault-tolerant architecture as compared to, say, the highly distributed, fault-tolerant MapReduce system on a distributed GFS or HDFS. So here is where the dichotomy comes in. When you're doing large volume analytical processing, which touches all the data, the parallel database architecture simply doesn't work. So where databases have been evolving over the past few years because of the big data technology that has emerged from the web is in two directions. On the one hand, we have the NoSQL databases, which are based on big data technology. They're called NoSQL because, firstly, they don't support full ACID transactions, or rather fully isolated serializable transactions in the traditional sense. Secondly, instead of having complex indexing, they have sharded indexing, which is essentially having partitioning of the data between different chunks or different blocks of disk. We'll come to sharded indexing shortly. Third, they don't support full joins. For a variety of reasons, they are restricted in the kind of joins that they can perform efficiently. And lastly, they support column-oriented storage if needed, so that for very long, wide columns, different parts of a record can be stored on different servers. The other side of database evolution is in-memory databases, which has been driven by the increasing volumes of main memory available on today's servers and the falling cost of memory. So today's servers have 64 gigabytes or even 128 gigabytes of main memory, which allows, for most practical purposes, many ordinary enterprise transaction systems to actually reside in main memory. So real-time transactions become possible at much higher rates than before. Varieties of indexes can be supported just as before in traditional databases, but now in memory, so different kinds of indexing structures are possible. And of course, complex joins are still possible. Of course, the data has to be still small compared to web scale petabytes of data or many hundreds of terabytes. But if you're talking about gigabytes of data, which a traditional enterprise transaction system rarely exceeds, in-memory database is a happy compromise where OLAP queries and all kinds of bulk data processing as well can be fairly efficiently performed. However, this is not the big data world. In the web, that doesn't quite work, and therefore NoSQL databases have become quite popular. We will study some of the NoSQL databases and the concepts very shortly. As far as in-memory databases are concerned, many of the techniques that worked in traditional databases simply carry over, except for the fact that because everything is in memory, one doesn't have to deal with the additional complexity of some parts of the index being cached versus being on disk and things like that.